Welcome back. Let's jump into task 4. By the end of this task, you will be able to work with the Minimax strategy on your own. Also, you will be able to solve two-player games where one player has the Minimax strategy and the other player follows the Maximin strategy. Please switch to the sheet Minimax Maximin solved. By definition, the motive of Minimax strategy is to minimize possible loss for a worst-case scenario. Essentially, it is the same as the Maximin strategy but used for losses. Also, note that it is mainly used in a zero-sum game scenario. We will see what is a zero-sum game in a while. You can see a 3 by 3 matrix in front of you, where player 1 has A, B, and C as strategies, and player 2 has X, Y, and Z as strategies. Notice that each payoff combination is the complement to each other. For example, CY has the payoff -2 and 2, which means the amount lost by player 1 is exactly the amount gained by player 2. This is true for each of the combinations. The sum of the payoffs always result in 0. This type of game is known as zero-sum games. Now we will proceed with this game. Let's say player 1 follows the Maximin strategy while player 2 follows the Minimax strategy. Again, as in task 2, we are going to solve for each player separately. There is a smaller matrix on your right. It is called the reduced form for a zero-sum game. Basically, it reduces the matrix in terms of player 1's payoff, since player 2's payoff is nothing but the complement of player 1's payoff. I could have used the reduced form to solve this problem, but I think it is better to use this form, which is similar to the template, to make each step more relatable. We will come to the reduced matrix at the end of this problem. We will begin with player 1 and solve like before. Let us note down the minimum gain for each case, and you can work along with me while I'm solving it. For first row, the minimum is 0. For the second row, the minimum is -3. And finally, for strategy C, the minimum is -2. The maxima of row minima are 0, that is the strategy A. Now let's look at player 2. First, we have to find the maximum loss for each strategy. For example, for strategy X, the maximum is -4. But we can type it only as 4. Since we are already calling it as loss, which accounts for the negative sign. Similarly, for Y, the maximum is 0. And for Z, it is 3. We need to find the minima of the column maxima, and the answer is 0, that is strategy Y. Now we will combine both strategies. Individually, player 1 will choose A and player 2 would choose Y, both having an equal payoff of 0. Now refer back to the reduced form. The combination of A and Y points at a single cell containing 0. In other words, their payoffs are the minimum of the row and maximum of its column, and it is called the saddle point of a matrix. In terms of game theory, if a saddle point exists, then it should be played. It is also a Nash equilibrium. So you have learned how to solve these type of problems. I would request you to pause the video and go through the practice exercise below. Once you are ready, we can check the solutions. How did it go? Let's check the solutions together. The minimum gains are and we'll find the maximum losses. You must have noticed that the row has a unique maxima but the column has 3 minima. Also, you can check it with the reduced form. And 2. The values are not same. So therefore, there are no saddle points for this matrix. A quick note: Minimax algorithms find its use in studying combinatorial games like tic-tac-toe or studying situations under certainty. In the next section, we will realize similar problems using the template. See you there.